So what we have here is a series of constructing binary tree from different traversals. We have in-order, post-order, pre-order, in-order, and lastly pre-order and post-order. It may start to look really weird at first, but once we start to understand the special property of each traversal, it's actually pretty simple and can be done within a few lines uh, through recursion. So let's look at this graph here. So given this is a binary tree we want, and the in order is 425, 425, 1, 6, 3, 7, and the post order would be 4, 5, 2, 6, 7, 3, 1. And right off the bat, we can see that given the special property of post order, we can always find a root at the last digit here, because post order guarantees that the root node is visited last. So right off the bat, we can root equals to tree node post order minus 1. And also we can see that the root node we just found, the one here, actually cleanly separates the left half and the right half of the tree by this one. And it is also pretty self-explanatory given the property of in-degree in order traversal, since the root node is visited right in the middle. Then what we can do is find this position is equal to in order dot index post order -1. So once we found this position, we now can start to sort of get the left side and the right side of the tree with recursion. In order, just leave out the actual index for now. I just lay out a basic structure. Oh, there's a typo. So root dot left, root dot right equal to self dot go tree in order post order, and I'll also return the root when this is done. And from here we can see that up until for the left side, up until the position, that's the part we want. And for the post order section, it's also the same, since in order the length of in order and post order is always the same. So let's write that down. Post and post. And for the right half, we can see that after the post we want is the desired part of the in order part, and this part is actually slightly different, and it starts from the post here, and you can see that 6th position here actually corresponds to the post. And we don't want the last part, since we already used it and it is the current root node, then that would be the in order part will start from post +1 up until the end, and the post order part will be post up until -1. So post up until minus 1. We also have to do a quick sanity check right here if in order, if not in order, so it means that we reach a empty one, so return null. And how this actually works is, I had an example right here. So we start off with 1 given this graph, and then we separate into 425 and 452, and the right side being 637 and 673. You can see immediately they are very similar as it should be, since the in-order and post-order consists of the same set of letters or digits, and if we take out this 1, the left tree and the right tree should still remain that property, and once we separate once more level, we can immediately see that they are right now the same letter, since they both have a length of 1. And we simplify that, we can get the original tree back. That would be 1, 2, 3, 4, 5, 6, 7. And it is actually pretty simple. And for time complexity, what we actually do here, let's analyze that together. We actually just loop, even though this looks like a recursion, the level of recursion we did was directly correspond to how long the in order traversal array is. So it will be O of n. And let's do a quick run. This is the empty scenario, and it works. And let's move on to pre-order and in-order. And this is actually pretty similar because we can see pre-order as a sort of flipped version of the post-order. So right now, so let's do the sanity check first. Pre-order turn none. And the root, like before, is the end digit of the preorder, following the property of that. And just like before, we get the in order middle position by getting the index from in order. So it will be preorder at position 0. And then we will lay out the structure like before. We'll just copy paste here. And we have to do a little bit of maneuver here. Pre-order, post, in order, pre-order, in order. And let's now analyze the index. So this is our original graph, and we're given pre-order and in-order, which is these two lines. And for pre-order, we want to start at position 1, since the first letter is the root node, and we don't want that. So we'll get 1 up until position plus 1, since this 3 corresponds to 6 right here, and that is 1 plus the position. So 1 plus that. And for in order, it will be everything up until position, since this is a Python list, and it will get rid of the last position. So this remains the same. And for pre-order, for the right part, we will want everything that is position +1, so here, and so that remains the same. And for in order, what we want is also position +1 up until the last character. So that will be empty. So let's do a quick syntax check. So if not preorder, return none. And actually preorder, since preorder will remain the same length as in order at the same time, it doesn't really matter which one we check in our sanity check portion. And then we get the root from the preorder, the first letter. That's the special property of preorder. And then we'll get a position just like the problem before. We want to get a separator between the left tree and right tree, and get the left from the index we just calculated, the right from index we also calculated, and lastly we'll return the root. Let's do a quick run. This is for sanity, and a little bit slow. It works. So like before, this there isn't really much space complexity to discuss since we didn't actually introduce any new data structure. And for time complexity, we can see this is a recursion, and the level of recursion we did is directly corresponds to how long the preorder or in-order list is. So that would be all of n, given we have n digits. And at each level, let me see, at each level, we're getting rid of one letters. So we're doing one or a constant number of operations. So overall, the time complexity will be all of n. So let's move on to the question 3 of the series, which is preorder and postorder. And this time, it is actually a little bit different from problem 1 and 2 because we don't have in order. So we do not get that middle separator like before. Instead, we get the first letter of preorder, which is guaranteed to be the root node, and the last letter of the postorder, which is essentially the same as the first letter of preorder. Then what we want to do is, so this is the graph we have, and this is the postorder, and this is the preorder. And we can see 1 and 1 at all time, they are guaranteed to be the same given the special property of both postorder and preorder. And once we get rid of that, we can see this 2 right here actually can serve as a separator between the left tree and right tree in the preorder section, because the left node of the root node in preorder structure, it is always guaranteed to be the first letter. And so once we get that, we can sort of use this index to track. Let me put it this way. And the letter after preorder is the left root node of the left subtree. And this 2 right here is guaranteed to be the end node in the postorder sequence, because in postorder 2 always comes last at the left subtree. So we can use the index 1 or the second digit here to actually marks the middle part, just like when we have an in order traversal sequence. So let's do that. However, there's also a tricky case here where we have to handle. So when we only have a length 1 sequence, then it will guarantee to be the root node. So let's do that. So first sanity check, if not pre, then return none. And then, like before, root equals to pre node and pre 0. You can also do post -1, they're the same. And if length of pre is equal to 1, so there's only one letter left, so there's no left or right here, so we actually just return root. And now we will try to get the position we mentioned before, and this will be the second letter's position in post order. So post dot index and pre second letter, so index 1, and we might consider add 1 to it since the property of Python list ends with the letter after the thing we want, so make it +1. And like before, we can now set up our recursion step. Like before, we just fill in that, then we consider the actual index. So we have the basic structure laid down, and then we were trying to figure out the index. And the post order is actually pretty simple. Like we mentioned before, 2 here actually serve the same functionality as the in order middle separator. So the post order will ends with plus. And for pre-order, since the first letter is the one we don't want, and so the letter will actually end 1 behind a post, which makes sense because pre-order and post order, so you can see them sort of as a shifted version, and so that would be +1. And for the right subtree, we can see here we don't want the last letter of post order, so it's from pos to -1. From pos to -1. And for the pre-order, we want from pos +1 to the end. So pos +1 to the end. And now we do a quick check. So sanity check right here. And like before, we set up the tree node. And if the length of the current pre-order is 1, we just return the current root. And if there's the length is 1, the longer than 1, then we can actually get the left and right subtree of the root. I'll try to run it. There's probably some typo. Let's do a quick check. So if not pre, if not pre, return none, and root equals to pre node pre 0. This makes sense. This also makes sense. And if length of pre is equal to 0 is equal to 1, then we'll return the root since they only have 1 digit left, and position is the post index. Pre the second letter That's why we want it to at least be length of 2 plus 1, and root the left equals self the construct form pre plus to 1 and plus, and right equals to construct form from pre plus 1 and plus to minus 1, return root. Let's see what the problem it is complaining. So 23 self.construct pre-post. So what it is complaining? Oh, could it be the thing here? It doesn't look like it. That shouldn't be a problem. Yep. Maximum recursion depth exceeded. So looks like we have a sort of a Stack Overflow problem here, and we built the tree node, and if length is equal to 1, then we will return a root, and if length is bigger or equal to 2, then we will get the index from pre and get the digit at pre, the second position, and get the index from this. This makes sense. And root the left equal to self the construct. There's no typo here. Pre from plus plus 1. Oh, there should be a 1 somewhere here. Yep. And let's run now. Okay, it works now. Yeah, what we are doing wrong is we forgot to add the 1 here, since the first letter of pre is the root node already used. And for space and time complexity is still very similar. For space, we didn't introduce any data structure, so we don't have to discuss that. And for time complexity, what we do here, we can skip this. It's actually just recursion of level related to n and being the length of pre, and at each level we only do a constant amount of operation, so that will be all of n. And so that's it for the 3 ways to construct a binary tree from different order traversal.